Hi, in this lecture video, I'll be discussing the synthesis of alcohol by the organometallic reagents. And there are three learning objectives for this video. First is to get ourselves familiarized and recognize the organometallic reagent. And second, to understand the chemical reactivity of the organometallic reagent. Why are they reactive? And why are one organometallic reagent more reactive than the other? And the third objective is to learn about the application of the organometallic reagent in the synthesis of alcohol. And that is our emphasis on the alcohol synthesis. So let's now go over the first learning objective: familiarize and recognize the organometallic reagent. What are organometallic reagents? Organometallic reagents are basically reagents that consist of carbon. So this is why we call this organo. So the term organo refers to an organic substrate that have the metal in it as well. So these are chemical reagents that consist of both the carbon and metal in them. And in these types of reagent right here, the carbon is negatively charged. And that is a very, very important concept and things that we need to remember. So in this case right here, the carbon are negatively charged, and therefore the carbon tend to behave as a nucleophile. So here is how we'll be able to recognize it. The organometallic reagent consistent of a carbon, and this can be any type of carbon that we want to. It can have one substituent, two or three, or whatever number of substituent on them. And now they bonded to a metal. And because we know that already that metal have low electronegativity, so whenever we have a carbon bonded to a metal, this bond right here, a lot of time, they actually have ionic character to them, in which the carbon is negatively charged, because carbon have higher electronegativity compared to this metal. So we can then think that the metal is then giving the electron to this carbon and making this bond right here become an ionic bond. So therefore have very high ionic character to it. And the resulting structure would then be following. The electron go to the carbon, and the carbon will become negatively charged, and the metal then become positive, producing our carbon ion. And we have all seen already that carbon ions are very reactive because they're very, very unstable. So they are very, very strong base, and they're very strong nucleophile as well. So these are very, very reactive reagent. And again, let me repeat this again. Organometallic reagents are very, very reactive. So therefore, as we work with them, we have to be very careful, because there has been numerous accidents that happen in chemistry lab when people work with organometallic reagent. So that's how we'll be able to recognize the organometallic reagent. And now let's go over the chemical reactivity of the organometallic reagent. And so the chemical reactivity of them are very similar to the hydride, the reaction of the hydride. So in the previous lecture, when we discussed about reduction reaction, we will then see that reduction reaction is whenever we have a hydride that is added to the carbonyl carbon, right? So in that process right there, hydrogen is then added to the carbonyl carbon, and then that is classified as a reduction reaction. So if we were to take our carbonyl derivative and react this with a source of hydride, the hydride will be added to this carbonyl carbon, producing this product over here, where we now have a hydride in there. So essentially, this is a reduction reaction. If we were to now take our organic substrate, maybe a carbonyl derivative, and now react this with a carbon ion, then the carbon ion will be react very similarly to the hydride. This is a good nucleophile. So now we'll come in and attack our electropositive carbon, carbonyl carbon in this case. And now the R group would then be added to the carbonyl carbon, very much similarly to how a hydride is then added to a carbonyl. But in this case right here, this R group right here is much more reactive than the hydride. And now we do not consider this reaction right here to be a reduction reaction, because it does not fit into the organic definition of a reduction reaction. Sure, electrons are being transferred in the course of this reaction. However, we do not classify this to be an organic reduction, because the organic reduction, as we recall, is basically at the reaction where hydrogen are then added to the organic molecule, or an electronegative atom, so an oxygen, are then being removed from the organic molecule. And if we were to be looking in the structure of the starting material and the product, we do not see hydrogen getting added, and we do not get to see of the removal of electronegative atoms to get the oxygen as well, because this oxygen is here and is still retained here in this case. So therefore, this, we do not consider this to be a reduction reaction. But principally speaking, then the reaction involving the organometallic reagent is very similar to the reduction reaction with the hydride that we have seen already. This reaction right here involving the organometallic reagent, which consists of the source of this carbon ion right here, are then referred to as the nucleophilic addition reaction. The reason why we call this nucleophilic addition reaction is because the reagent is behaving as a nucleophile. And second, we are adding this to the carbonyl carbon. So therefore, this is called the nucleophilic addition reaction, or addition of the nucleophile to this substrate right here. And in this case, this is the carbonyl carbon. Now, so how do we then generate our carbon ion? These are very, very reactive. So how do we make something that is so reactive? And here are some of the explanation right here. Some of the method how we be making them. But before we go over them, it's important for us to again discuss the reactivity and learn how to recognize the organic metallic reagent. Again, they consist of a metal bonded to a carbon. So what kind of metal do we have? So here in this case right here, this is a list of different metal and different elements from the periodic table. And some of the metal that are very common in the case of the organic metallic reagent. This metal right here, a lot of time are lithium and magnesium. And we can also have copper as well. And so the lower the electronegativity of the metal that is bonded to the carbon, the more negative the carbon would be, and therefore the more reactive it would be. So, and these are some of the electronegativity of some of this metal. We can then see that lithium have a very low electronegativity. And therefore, if we were to have our carbon bonded to the lithium, then that means this carbon right here would have a very high electron density on it. And that makes this reagent right here very reactive. And again, please remember this. The lower the electronegativity of the metal bonded to the carbon to form produce a particular organometallic reagent, then the more reactive that carbon reagent would be. And if we were to have a metal instead of lithium, and now we have magnesium, magnesium has a higher electronegativity than the lithium. So in this case right here, organometallic reagent involving the magnesium would not be as reactive compared to the organometallic reagent consistent of the lithium. And if we were to now do a comparison, and another one of the types of metal that are very common in the organometallic reagent would be the copper. So in this case right here, copper. And if we were to be looking at the electronegativity of copper, it is 1.75. So this, you basically have high electronegativity compared to lithium and magnesium. So therefore, we can see organometallic reagent consistent of copper would then be less reactive. And the less reactive it is actually may be more desirable, because now it means it can react selectively. And organometallic reagent consistent of copper, we call them cupric reagent, versus organometallic reagent consistent of lithium, are called the alkyl lithium reagent, versus organometallic reagent consistent of the magnesium as the metal, are then called the alkyl magnesium reagent, or also called the Greggnard reagent, named after the chemist who invented and who studied this reagent right here. And now, let's now go over the chemical reactivity of organometallic reagent. There are again very strong bases and very strong nucleophile. So whenever we use organometallic reagent, we do not want any polar product in it. And in fact, we cannot use a polar product to prepare our organometallic reagent, because this reagent right here will react with a polar product solvent. So the carbon ion is again very strong nucleophile. and very strong base. If we were to take our organometallic reagent and treat this with an alcohol, then now if the organometallic reagent or the carbanion will then come in and pick up the proton from the alcohol to convert this into the corresponding alkane and produce our metal alkoxide. And if we were to look at the difference in pKa, this pKa right here is anywhere between 17 to 18 versus this pKa of this corresponding alkane is 50. So you can see equilibrium is very much shifted to this product side right here. So that means this reaction right here will be a very fast and reactive reaction. So please keep that in mind. Organometallic reagents are not compatible with polar product solvent. And now let's go over one of the types of organometallic reagent, the Grignard reagent. This is a very common types of organometallic reagent. And this Grignard reagent right here is then characterized by the presence of a carbon-magnesium bond. So the magnesium is then being used as the metal. And this can be prepared by having an alkyl lithium treated with a magnesium metal in it. How we will prepare this is as follows. Now, it is quite simple for us to make our alkyl halide. And once we have made our alkyl halide already, we will then take this and treat this with the magnesium solid or magnesium metal. And so in this process right here, once we take this alkyl lithium, this alkyl halide, treat this with magnesium, we will be able to produce this Grignard reagent right here through a chemical reaction. So this reaction right here is then referred to as an oxidative addition reaction. And principally speaking, this is how it would work. Now we can imagine the following. The bond between the carbon and the halogen here. This is not a very strong bond, right? Because this halogen is constantly pulling an electron away from this alkyl group right here. So this is not a very strong bond. But this alkyl group consists of carbon in it. And carbon itself, it actually have an electronegativity of 2.5. So it's not very, it do not want to give an electron to the halogen that well either. So you can see this will be a weak bond right here. So the halogen want the electron from the carbon. But the carbon, it also want electron as well because it is an electronegative atom. So it will not be a strong bond that exists between this carbon and this halogen. So when we take this molecule right here, with this bond right here, they are not very strong, and we then treat the magnesium with it. Magnesium is a metal, and it has 2 valent electrons on it. And you really want to give those 2 valent electrons away. So magnesium is a metal. So therefore, this is where the magnesium would come in. It would be the analogy as follows. These 2 atoms right here are fighting for electron over the electron in this covalent bond. And now the magnesium has electron. They will be very willing to donate. So in the end, what happened is that the magnesium will be given 1 electron to this carbon on this alkyl halide reagent and another electron to this halogen right here. Therefore, effectively break up the bond between this carbon and this magnesium. So magnesium is inserting itself in the metal. So this is why we call this an oxidative addition, meaning it gets inserted in and now it gives an electron to the reagent. So this is why that in the end we call this an oxidative addition reaction. So magnesium will be able to then insert itself by giving 1 electron to this halogen and another electron to this carbon right here, or this alkyl group. So this bond right here, even though that we draw them together as a covalent bond, but they have ionic character to them, in which the following: the charge on this magnesium is +2, the charge on this halogen is -1, and the charge on this carbon on the alkyl halide is then -1. So that's how the electron density and the charges on this organometallic reagent would be. And a lot of time we can also represent this as follows: R negative, and then so such as this one, R negative, followed the magnesium +2 and the chloride -1. So this is another way how we will be able to represent the organic metallic reagent. And the one thing that is very important for us to notice here is that this carbon right here is negative, and we have ourselves the carbon ion. So that's how we can actually generate the carbon ion. It is generated from the alkyl halide, treating that with the magnesium reagent to now produce the carbon ion. And one of the factors that is really important that we need to discuss here in this class right here, which is something very powerful and something really cool that happened in this reaction right here, that is very important that I point this out to all of you. And that is the following. In the course of the making of this organometallic reagent right here, or this Grignard reagent, there's something really cool that is happening right now. And that is basically the polarity of the carbon has been inverted. If we were to be looking at our starting material here, in this case right here, the charge on this carbon in the case of the alkyl halide, it is partially positive. So that's what it is. And a function would then be a good electrophile, right? So this carbon right here have electrophilic character to it. But once we take this alkyl halide, treat this with magnesium to produce the Grignard reagent, the carbon now will be changing its polarity. And this is something we call unpoling. Unpoling means that the polarity is changed. So unpoling. In which now the charge of this carbon, after it reacts with magnesium, it now becomes negative. So now the carbon changes its polarity and it now have a nucleophilic character to it. So this is pretty cool right here because it completely changes the property and the chemical reactive activity of the carbon. So that's something very important that we need to point out. Now, if we were to have an aromatic halide, such as in this case right here, this chlorine bonded to the benzene ring, we can also convert this into the Grignard reagent as well. So this happens for normal saturated hydrocarbon and the unsaturated hydrocarbon as well. So if we were to have an alkene, we can also convert this into the Grignard reagent as well. So there are many different types of Grignard reagent that exist out there. Pretty much anytime we have an alkyl halide, we can change that into the Grignard reagent by treating this with magnesium. And in the organometallic reagent, such as the Grignard reagent, the reagent are then coordinated to the solvent. And this helps them with this stability. So a lot of time we'll be using a polar A product solvent in the synthesis and the preparation of the Grignard reagent. So in this case right here, once this magnesium right here becomes positive 2, it then coordinates to the electron from the oxygen from the solvent. This helps stabilize this and therefore allow us to make this reagent. And now let's go over the reactions of the Grignard reagent. When we take the organometallic the Grignard reagent and we treat this with our ketone or aldehyde, then it will react very similar to the case of the hydride, except now instead of adding the hydrogen, we'll be adding this R group or this carbon ion. So if we were to have this, and we now know that the ketone and aldehyde are good electrophile because this carbon right here is partially positive. So that's a good electrophilic carbon. And when we take this and treat this with the Grignard reagent, again, depending on what this R group will be. It can be any alkyl group or maybe it can be a vinyl group as well, in case it is a double bond. And this, it becomes negative, so this acting as a nucleophile, come in, attacking this carbon. So the mechanism is as follows. The Grignard reagent produces this carbon ion. This carbon ion is acting as a nucleophile. Come in, attacking this carbon, exceeding octave of this carbon, so therefore we have to break up one of the pi bond and the electron, then go to the oxygen. So initially, we'll be producing this alkoxide right here. And this alkoxide is then coordinated with the magnesium reagent to form as a counter ion. So now we are producing our alkoxide. And on the next step, when we add in water, so this will be the step number 2 right here. So this is the first step, and this is the second step. When we add water or a polar product solvent in, then now the alkoxide would pick up the proton from water or another polar product solvent and convert this into the alcohol. If our carbonyl derivative is a ketone, we'll be able to produce the tertiary alcohol, because another alkyl group is then added to this carbon right here as it converted into the alcohol, so become a tertiary alcohol. Versus if we were to have an aldehyde, we'll be able to change that into a secondary alcohol. So that's the types of reaction and the type of alcohol that we can make. Whether we are making a secondary or a tertiary alcohol is then dependent on the structure of the carbonyl derivative that we are starting out with. And again, please note the following. Water is then added to a flask in a separate step, the second step right there, not on all together in one reaction flask. And now let's try some of this example right here to make sure we know how to react, how to recognize and predict the products involved in the Grignard reagent. So in this case, we have our ketone reacting this with first the methyl, so we call this the methyl Grignard reagent in the presence of ethyl ether, because again we have to use this solvent to coordinate to this solvent to stabilize and making it, followed by treating this with water in a separate step. So what will be the product? So in this case right here, please recognize that this is our nucleophile right here, so that is our carbanion, and that will be the group that will be added to this carbonyl carbon. So this is our R group right here. So in this case, we'll be able to convert this, add this to the carbonyl, and that will then change this into an alcohol. And now the methyl group, or the carbanion, whatever it is, in this case the methyl group, that will then be added to this carbon. And that will be the product of this first reaction. And now let's try a few reactions right here. Let's try this reaction number 30. So when we start with this, so this is called a vinyl halide. Vinyl simply refers to the fact that this have a double bond in it. So if we were to take this start with this vinyl bromide or vinyl halide with first magnesium, followed by treating this with acetone, followed by water, then what will be the product of this reaction? So here in this case right here, let's go over this. So when we take this and treat this with magnesium, we'll be able to convert this into the following. A Grignard reagent. So we'll be able to convert this vinyl bromide into the Grignard reagent. And now on this Grignard reagent right here, then it will be this carbon right here that is negatively charged. And when we now take this and treat this with acetone or a carbonyl derivative, then now this whole, so this bond here will be broken, and the electron go to this carbon, making this carbon the nucleophile, and that come in and attack this carbonyl carbon right here. So in this case right here, we'll be able to produce the following. So this carbon is this carbon, and now the carbonyl carbon, right? So this will be the carbonyl carbon right here, and that have an oxygen bonded to it and the two methyl group bonded to it. So that will then be the structure of the product, followed by the protonation step. And now let's try this example number 31 right here. When we take a carboxylic acid and we react it with the Grignard reagent, followed by acid workup, what would be the products? So here in this case right here, you will be surprised to find the following. There will be reaction, except the product would not get changed in any way, because there are multiple reactions that will produce the same thing again. Here in this case right here, when we take this Grignard reagent and we are reacting this with the carboxylic acid, the carboxylic acid has the proton that is not compatible with the Grignard reagent, right? Because this is an acid right here. And now this reagent right here, it can behave as both a nucleophile and a base. Acid and base reaction happen a whole lot faster than nucleophilic addition. So here in this case right here, the acid and base reaction will be the major reaction that will happen first, where this Grignard reagent will be behaving as a base to come in and pick up the proton from this carboxylic acid, and therefore deprotonating this carboxylic acid right here. So we have that. and we have methane gas. Because this, when this pick up this, it becomes methane. And now we still have our Mg, our Grignard reagent they left in here. So that will be the product of the first step right there. Once we have deprotonated this already, then now let's say we were to have excess Grignard reagent. Will the excess Grignard reagent be able to come in and do another addition of this carbonyl carbon right here? And the answer is no, because once this has been converted into this carboxylate right here, this carbonyl carbon on the carboxylate is no longer a good electrophile. So not a good electrophile. So even if we were to have excess Grignard reagent, it will not be able to come in and attack this carbonyl carbon right here. So the reaction pretty much would get stopped once we produce this salt right here. And on the next step, when we treat this with acid water, then the carboxylate will now act as a base, and that come in and pick up the proton from the acid and become the carboxylic acid again. So yes, there will be reaction, but nothing will get happens, but no new product will get produced in the course of this reaction. So that will be the chemical reactivity of the Grignard reagent on aldehyde, ketone, and the carboxylic acid. Now, how does the Grignard reagent react with ester functional group? Then here is what happened. The Grignard reagent will be able to add twice to the ester, and that will be able to convert this into the tertiary alcohol. So for an example, here in ester right here, when we take this and we treat this with the Grignard reagent, even if we were to have one more equivalent of the Grignard reagent, it will react twice. So please keep that in mind. And it is not possible for us to stop after we added only one of the carbanion to the carbonyl carbon here. But then the reaction, even if we have only one equivalent of it, it will be able to come in and react further again. And the mechanism of this reaction as follows. Again, so the carbanion from the Grignard reagent will come in and attack this electrophilic carbon right here to convert this into this intermediate. And now this group right here, it is a decent leaving group. It is not the good leaving group, but it is a decent leaving group. So it can leave, and the electron from the oxygen is donated back now, kick off this leaving group right here to now produce our ketone. But it's not possible for us to stop at this ketone right here, because the ketone carbonyl is even more reactive than the ester carbonyl. So therefore the remaining Grignard reagent will come in and react with this ketone first before it come back and react with this ester. So therefore another carbanion from the Grignard reagent will come in, do another attack again on this carbonyl carbon and producing this alkoxide, follow on the next step, the protonation step. That is now how we have convert this into a tertiary alcohol. So the ketone would then be converted, the ester would then be converted into the tertiary alcohol when we treat this with the Grignard reagent. And now let's focus on the reactivity of the Grignard reagent with the carboxylic acid one more time in great detail. Now we have seen the reaction of the carboxylic acid already on one of the example 31 that we have discussed previously, and now let's get into this in more detail. So the Grignard reagent will not be able to add to the carbonyl of the carboxylic acid. Please keep that in mind. Instead, it will undergo acid and base reaction rather than nucleophilic addition with the carboxylic acid. So again, here's an example. Here is our carboxylic acid reacting this with the Grignard reagent. So the Grignard reagent will behave as a base. And now pick up this proton right here. So we have acid and base reaction that is happening. And of course producing our alkene and this resulting carboxylate salt right here. And for this similar reason right here, it is not possible to form the Grignard reagent in the presence of even a mildly acidic proton, such as the hydroxy group from the alcohol functional group. So please keep this in mind right here. It is not possible for us to produce the Grignard reagent in the presence of an alcohol functional group. So if we were to basically hope to convert this functional group right here into the Grignard reagent to make this carbon right here behave as a nucleophile, we will not be able to do that. And the reason why is the minute that we react this with the magnesium to convert this into the Grignard reagent, this Grignard reagent right here will then come back in and grab this proton right here from the alcohol functional group. And now we are basically depleting or destroying our Grignard reagent. So this would now become an CH3 group in here in this case. So it's not possible for us to create the Grignard reagent in the presence of a alcohol functional group. And here is another example right here in which that we will not be able to produce the Grignard reagent. Now we are not able to produce the Grignard reagent of what we want simply because after we make it, it will react with itself and therefore depleting the Grignard reagent that we are hoping to make. So here in this case right here, if we want to convert this alkyl of this halide right here with the ketone functional group in it into a Grignard reagent, then we'll not be able to make what we want. Let's say here's what we want right here. We will not be able to make it. Even though that it will, the magnesium will be able to undergo the oxidative addition to insert itself and convert this into this reagent initially. This reagent will then come in and react with another molecule of the reagent, or maybe the carbonyl of a different molecule of this what we have seen right here, and that would then depleting this Grignard reagent of what we want. So please keep that in mind right there. So carbonyl and alcohol within the Grignard reagent is not possible to make.